Ever stop and think about how an AI actually thinks? Well, today we're going to pull back the curtain and peek inside the mind of a computer as it solves a puzzle. We'll see how these systems navigate a massive, invisible maze of choices to do everything from finding the fastest route to your house to understanding what you're saying. I mean, think about it for a second. You ask your phone for directions, and boom, almost instantly it gives you the optimal route. Not just a good one, the best one. How on earth does it sort through a bazillion different possibilities to find that one perfect path so fast? That's the exact question we're tackling today. You see, for us, it's just a drive. But for a computer, it's a huge problem. Every single intersection, every road, every potential turn is a branching path. It creates this gigantic web of possibilities that computer scientists call a state space. The AI's job is to intelligently explore this invisible maze and find that single best path from point A to point B. So how does it navigate this maze without just wandering around forever? It can't just try every single road. That would take ages. It needs a strategy, right? A way to search smarter, not harder. And this is where we meet our first big idea, the power of a heuristic. To make this all feel a bit more real, we're going to use this classic AI search problem. The goal is super simple. Find the absolute best driving route from the city of Arad to Bucharest. Here, the cities are our choice points. The roads are the paths, and those numbers, that's the actual driving distance. This map is our maze. Now, you could try to search this map blindly. An uninformed search is kind of like trying to find your keys in a pitch-black room. You just pat around everywhere until you bump into them. It works, eventually, but an informed search, that's like someone handing you a flashlight. It gives you a sense of direction. It's a total game changer. And that flashlight, that guide, is what we call a heuristic. It's basically a rule of thumb, an educated guess that helps the AI make smart choices. For a map problem, a brilliant heuristic is the straight line distance, as the crow flies. It's not the actual road distance, of course, but it gives the AI a really powerful clue about which way it should probably be heading. Okay, let's see this in action with an algorithm called greedy search. It's called greedy for a reason. At every single step, it just selfishly picks the option that looks best right now, based only on that heuristic. It doesn't really think long term. So we're at Arad, and our heuristic says we're about 366 kilometers from Bucharest. So from Arad, we've got three choices. The greedy algorithm completely ignores how long the road is to get to those cities. It only cares about one thing. Which of those next cities is closest to Bucharest in a straight line? And the winner is Sibiu, with a heuristic of 253. So that's our move. We greedily head to Sibiu. All right, we're in Sibiu. We asked our heuristic compass again. Out of all the next possible moves, Făgăraș is the closest to Bucharest as the crow flies, just 176 kilometers away. Let's go there. We seem to be making fantastic progress, right? We're getting closer and closer, homing in on our target. And from Făgăraș, there's only one place to go, Bucharest itself. The heuristic value is now 0. We're there. The algorithm found a path, Arad to Sibiu to Făgăraș to Bucharest, and it found it really fast. Looks like a success, right? But is it the best path? Nope, not even close. The route our greedy search found is 450 kilometers long. But if you look carefully, there's another route through Râmnicu Vâlcea that's only 418 kilometers. Our educated guess, our heuristic, led us astray. It took us down a path that looked great at every turn, but wasn't the best overall. And that's the big weakness of being purely greedy. So if being greedy doesn't always work, how do we find the absolute, guaranteed best every single time? Well, this brings us to A-star search. And let me tell you, this is one of the most important, most famous algorithms in all of AI. It's the gold standard for finding the optimal path. The genius of A-star is this beautiful little formula. It doesn't just look at the heuristic, H of n, or guess about the future. It also pays attention to G of n, the actual cost of the path we've already taken. It's like it balances the past, what we know for sure, with the future, our educated guess. And that balance is what makes it so incredibly smart. But for A-star to work its magic, for it to guarantee the best path, our heuristic has to follow one simple golden rule. It has to be an optimist. It can never, ever overestimate the true cost to get to the goal. Because if it did, A-star might ignore a path that's secretly the best one just because the guess was too pessimistic. This optimistic quality has a name. It's called being an admissible heuristic. As long as our heuristic never overestimates reality, A-star is mathematically proven to find the best possible path. Our straight line distance is the perfect example, right? The shortest distance between 2 points is a straight line. Any real road has to be that long or longer. It's just a simple, elegant rule that gives A-star its incredible power.
Okay, so far we've seen how an AI can find its way through a maze by following a very specific step-by-step recipe. But what if there's another way for a computer to think? What if instead of giving it instructions, we just told it a bunch of facts and let it figure things out for itself? This is a totally different way of thinking called the declarative approach.
What we've been looking at, like A-star, is procedural. We tell the computer exactly how to solve the problem. But a declarative language like Prolog flips that on its head. We don't tell the computer what to do, we just tell it what's true about the world. We give it facts and rules, and it's up to the computer to connect the dots. So instead of writing some complicated function, we just build a little knowledge base of simple truths. Arid is connected to Sibiu. Check. Mary likes tea. Got it. John also likes tea. Check. We're not giving commands, we're just describing the world. And from this, the computer can actually answer questions and figure out new things we never told it directly.
Now, at first glance, these two methods, the procedural search and the declarative reasoning, they seem like they're from different planets. One is like following a recipe step by step. The other is like being a detective with a bunch of clues. But here's the cool part. They share a secret, powerful mechanism under the hood.
And that secret is called backtracking. It's so simple yet so powerful. When a search hits a dead end or a line of reasoning leads to a contradiction, the system doesn't just throw its hands up and quit. No, it intelligently goes back to its last decision point, and it tries a different path. It learns from its mistakes on the fly. This slide shows it perfectly. We ask Prolog, hey, find me something, call it X, that Mary likes, and John likes. So first, it finds that Mary likes food. Then it tries to prove the second part. Does John like food? It checks its facts. Nope, dead end. But here's the magic. It doesn't give up. It backtracks. It goes back, scraps the food idea, and looks again for what Mary likes. Ah, she also likes tea. Now it tries the second part again. Does John like tea? It checks its facts. Yes, he does. Success. That ability to go back and try again is what makes it so smart. All right, we've talked about heuristics, optimal search, and this wild connection between following instructions and reasoning about facts. But why does any of this matter? Well, because these aren't just clever programming tricks. These are some of the absolute bedrock, foundational ideas of all of artificial intelligence. So let's nail down the big takeaways here. 1. Heuristics are the compass that lets AI solve massive problems without getting lost. 2. Admissibility is the magic ingredient, the mathematical promise that guarantees a perfect solution. And 3. Backtracking is this universal problem-solving skill, the ability to recover from a mistake and try again. These ideas are the engine that powers everything from robots navigating a room to the natural language models that are changing our world. So, the next time your GPS spits out a route, or you ask a digital assistant a question, just take a moment and think about what's really happening under the surface. It's not just number crunching. It's a sophisticated, logical exploration of a vast, invisible maze of possibilities. It really makes you wonder, doesn't it? Where does simple computation end and real problem solving begin?